So with this, I will thank you a lot for your delivery and hope to collaborate with you in future. So having saying so, we will move forward in this session. Next, we are having another keynote from Professor Feng Hao, and in this session, Dr. Nabarun Bhattacharyya is going to chair the session. Dr. Bhattacharya is a Senior Director C-DAC, Kolkata. So I would request Dr. Bhattacharya to kindly take the stage.
Good afternoon.
Over to you.
Good afternoon to all the delegates for the conference.
I think Dr. Giri, before this start, Dr. Giri, are you there? Dr. Devashish Giri is there? Dr. Giri? Can you just tell Feng Hao sir will be here or not?
Just to check, because it's a few times before I have seen that he was there.
Yeah, but I cannot see. Nabarun sir, I cannot see the speaker.
Okay.
Just wait a few minutes.
Sir has just joined.
Okay. Thank you.
So should I continue?
No, join. Devashish. Feng has joined. Feng has joined.
Welcome, Professor Feng.
Hi,
Welcome,
good morning or good afternoon.
Good afternoon. Can you remember me?
Yes, you look familiar.
Yes.
Oh, yes.
Yes, we are
You
there
are,
in the
I remember you work on the HP access.
Yes.
Feng.
Hi, sorry,
Hi,
I only had 1 hour for today's talk because it's a busy day for me.
No problem. We are starting now immediately. So Professor Nabarun Bhattacharyya, please introduce our speaker, Professor Feng. Yeah. Thank you, sir.
Yeah. Very good. Good morning and good afternoon to all the delegates. And we are going to start the session. We are very fortunate to have Professor Feng Hao, who is a professor of security engineering at the Department of Computer Science, University of Warwick. He received his PhD in 2007 in computer science from the University of Cambridge. He worked in the security industry for a few years before joining academia. With colleagues, he designed a few cryptographic protocols: AVNet, OVNet, JPEG, YPEG, DREI, DREIP, and SEAL. Among them, JPEG with Peter Ryan has been adopted by the thread group as a de facto standard to perform the IoT commissioning process used in Google Nest, ARM Embed, NXP, D-Link, Qualcomm, Samsung, and Texas Instruments, etc., and standardized in ISO IEC 117704 DREIP with CMAC. Dusty was successfully trialed in Gateshead during the UK local elections in 2nd May 2019. His 2006 paper with Ross Anderson and John Dowman on combining crypto with biometrics effectively in IEEE transactions in computers is ranked the top in Google Classic papers in the category of cryptography and computer security. His work on self-enforcing e-voting has led to a €1 million ERC starting grant and an ERC proof of concept grant with Peter Ryan. He co-edited a book called Real World Electronic Voting, Design, Analysis, and Deployment by CRC Press. So we are very fortunate to have you, Professor Feng, and we are very eager, along with our delegates, to listen to your talk on the topic an overview of password-authenticated key exchange protocols. So time starts for you now, Professor Feng.
Okay, thanks, Nabarun, for the kind introduction. Let me try to share my screen. Okay, can you see my screen?
Yes, we can see your screen.
Yeah, I have to apologize in advance because I have another meeting in half an hour. So I probably only have time to go through part of this talk, not the full talk. Apologize for that. So yeah, I'm Feng Hao. So this is just a quick outline. I'm going to briefly introduce to you this problem called PAKE, Password-authenticated key exchange. There are a lot of research in this area, so I'm going to give a taxonomy and overview of the field. Recently, there was also an IETF selection to choose the PAKE for standardization. If I have time, I will also briefly touch on that. So part of this talk is based on an SOK paper recently I wrote with Paul van Oeschot. So the link to the paper is here. If anyone is interested, you can have a look. So let's start from 1976. Everyone knows that this is a breakthrough in cryptography. So Diffie and Herman, they invented, basically they proposed a new direction in cryptography. What they propose is a groundbreaking protocol called Diffie-Hellman key exchange protocol. So Alice and Bob, they simply exchange some public keys over the air, and then in the end, they can compute a session key. And if the attacker, they simply eavesdrop the traffic, they cannot compute the session key because of the one-way property of the discrete logarithm. So this is all great, but the protocol has a fundamental weakness. So the protocol establishes a session key with two parties, but you don't really know who you are sharing the key with. So that is because the protocol doesn't have authentication, and concretely you can have a man-in-the-middle attack. So someone in the middle, they intercept messages, then they can change the ciphertext so that you encrypt all your encrypted messages will be decrypted by the man in the middle, and then re-encrypted before sending out. So as a two parties, they don't know that their messages have been recorded. So this is a well-known problem. The question is how to solve this problem. This actually turns out to be harder than what people had thought. There are over 40 years research on this topic, and today is still an active field. So on a big picture, how do we solve this problem? The fundamental issue with Diffie-Hellman is no authentication. So the idea is quite intuitive. Let's add authentication. And in security, as we know that there are three factors to do authentication. Something you know, that is password, something you have, that's a token, typically that will store a pair of public and private key. And the third one is biometrics. So there works in each of these categories. The first one is called password-authenticated key exchange. Second one is called public key authenticated key exchange. Sometimes people simply call it authenticated key exchange. But here, just to distinguish from previous PAKE, I call it PK AKE instead of AKE. The last one, there's some work, but not much, partly because biometrics is not secret. So these are the three main approaches. Today, I'm going to talk about the first one. So what is password-based key exchange? If we look at a balanced PAKE case, you call someone, and if you pick up your call and call someone from US, for example, it's almost guaranteed that your phone call is going to be recorded, because a service provider, they can access to your phone conversation very easily. This is a phone tapping. Everyone knows about it. Usually, in different countries, there are regulations in place to prevent misuse of phone tapping to protect citizen privacy. For example, in the US, you cannot just tap the phone call of a US citizen, but the law is different if you use it to tap non-citizen. For example, if you call someone in another country, if the call goes through the service provider in the US, then if you are not US citizen, then there's no obligation that service provider will respect your privacy. So the PIC was trying to solve this problem. Both parties, they can share a short secret, and that is a short code, a 3-digit code, for example, 10-bit. And then based on this short digit code, you simply enter it to your phone pad. Then the software will do the key exchange and establish an end-to-end secure channel, so no one can eavesdrop your phone call. That's motivation. And the key thing here is that there's no trusted third party and no public key infrastructure. So this problem was not long possible until 1992. So remember, the Dept was invented in 1976, so it was not until 1972, so that's more than 10 years later. Then some people realize, Belleving and Merritt, they realized that this actually is possible to solve this problem. At the time, they were researchers at a phone company, so you can see actually that is motivation why they want to work on this problem. For the first PIC solution is called EKE. And that has 3 variants: RSA, based on RSA, Algoma, and Dept. So the RSA version was considered insecure for many reasons. And one of the reasons is the main reason is because of the ISA modulus. You cannot encrypt my ISA modulus use a password. You have to send it in the clear. And because you send it in the clear, the attacker can freely manipulate this value. So that gives a lot of problems. And one way to try to solve the another problem with modulus is that generating the ISA modulus is very slow. Some people propose to cache their ISA modulus, so generate once, but use it in several sessions, but that will defeat forward secrecy. So these problems are fundamental and difficult, almost impossible to solve. So for this reason, if you look at the practical applications of PIC, almost all of them are based on discrete logarithm, not based on RSA. So this is the classic version of the EKE, called the Dept version of EKE. Basically, you have Alice and Bob, they do a Dept key exchange. And in addition to that, Alice and Bob, they simply use a password to encrypt the data. That's very simple, straightforward change. But if you use password to encrypt data, and the data here is essentially a public key, but public key is not random data, it has certain structure. So that gives a problem that someone can simply use a random password to decrypt this value, and then see whether decrypt value can satisfy certain property. So that allows attacker to filter out certain password. In other words, if you use DHEKE, then you will leak information. So that was a problem discovered by Jasper in 1996. That actually was 4 years later. So in 2000, there was a very famous paper by Bila, Ponchiva, and Logwe, and this paper was very widely cited in the field. Basically, the conclusion in the paper is that they prove that EKE is secure, protocol is provably secure. That's interesting, but on the other hand, so that is a theory, but you also need to think about practice. On practice side, we already know in 1996 that in 1996 that EKE has problem of information leakage, but then in 2000 there's a model to prove that EKE is provably secure. So apparently there's a mismatch here. So what's the catch here? The catch is assumption in the proof. The researchers they assume this ideal cipher. And they assume this ideal cipher doesn't leak any information, even you use a low entropy key. So that is assumption, but they don't have a concrete cipher. And as later on, Bila and Logway, they try to propose some concrete constructions as part of the IEEE standardization process. And one of the constructions they propose is a very simple one. So simply, if you want to encrypt a group element, you simply use group element times hash of the password. Again, this also raises questions. The question is, what is hash here? Hash is, they say hash is a random oracle, but you cannot use a one-way hash function, because if you do that, then it's trivially insecure. So it has to be a different function and it has to satisfy certain properties. Again, that is another assumption. It's not something concrete. In fact, if you read the original submission, even the authors themselves were not very entirely sure whether this will work. They propose it, but they hope it will work. But later on, some researchers, they analyze the constructions proposed by Bila and Logway, and what they found is that none of the constructions was actually practical. And for this reason, EKE was not included in the IEEE standard. There were 8 years. So EKE was proposed for standardization, but you need to define this ideal cipher. And for 8 years, that construction was not done. So in the end, it was not included. What we could learn from here is that I think it's the importance of complete specification. Sometimes we see a protocol has a lot of secret proofs, but the proof makes certain assumptions on certain construction blocks that do not exist. So that create a mismatch between the theory and the practice. If we want to have secret proofs to have concrete meaning, then the specification needs to be complete. So the problems with EKE actually motivate a different designs of the PEG, and one of the most famous one is called SPEAK. The idea was quite simple. Simply still follow the Diffie-Hellman approach, but instead of using password as an encryption key, Jasper proposed to use password to derive a generator. So the protocol is basically the same as Diffie-Hellman, but the new thing here is F function. So basically you take F, you take input as password, and you use this F function is called hash to group function. And that will generate a base. Once you have this base, then the rest is the same as Diffie-Hellman. If you look at this protocol and you read the original paper, the claim is that you only need two explanation. And that is incredible, because if you think about the Diffie-Hellman, even with a plaintext Diffie-Hellman, and if you consider using the DSA group to implement Diffie-Hellman, you actually need 3 explanations, including one to validate the public key. But here you only need 2 explanations. So even more efficient than unauthenticated Diffie-Hellman. Clearly, this doesn't make common sense. So because it sounds too good, then you need to be careful. But however, this has been frequently ignored or neglected in the past. People simply say it has 2 explanations, so it's superb. But actually, we need to look into exactly what are these 2 explanations. So the key thing here is a hash to group function. In the original paper, Jasper proposed to use a safe prime, and there's a particular reason why you use a safe prime, not use a DSA. And he proposed simply use the password as the base, a password raised it to the power of 2 as a base, but that was found insecure. Later on, during the IEEE standardization, he proposed to add another hash function to solve the problem. Once you have another hash function, then there's another issue, because the modulus is a safe prime. So if you use 3072-bit P, then the exponent, the size of the exponent is 3071 bit. So if you compare with the explanation in the DSA group, it means that one explanation is actually 12 times more expensive than the explanation in the DSA group. So that is actually a huge difference. So if you simply count the number of exponentiations, this can be very misleading. But somehow this important detail has been frequently neglected by people, even people working on the field. How to address this long exponent? This problem was recognized as early as in 2000 during the IEEE standardization. So in the original proposal, Jasper proposed to use a safe plan, but later on in the IEEE standardization, they tried to generalize it to use DSA group. And simply you redefine the F function, and you still use a hash. But there are two issues with the function in the IEEE standard. The first one is that this function doesn't guarantee you always get the right output or valid output. Sometimes you may get invalid output. If that is the case, then the function simply gets stuck. You cannot just redo the function, because if you do that, then that also defeats the constant time operation principle. So that is one such issue. Another issue is that now the F function becomes very expensive, because if you want to compute the base, then the F function will have 2,815 bit on the exponent, and that is very expensive. So if we look at in the table, and if we look at this implementing SPIC with different settings, you will see that in general you use DSA group. That is more efficient, because it takes essentially so one exponentiation to generate public key, and one operation to validate public key, and one operation to compute the computer session key. But you should see that actually the operation of hashing to group, this actually dominate the whole operation. So overall, the cost is 11 exponentiations. So now you can have a fair comparison with Diffie-Hellman, unauthenticated Diffie-Hellman. So unauthenticated Diffie-Hellman has 3 exponentiation, but SPIC actually has 11. So it's 3 times more more expensive than Diffie-Hellman. That actually makes sense, because security is never cheap. It has cost. But you can see that SPIC is actually more expensive than Diffie-Hellman, not the other way around. And another tricky thing with SPIC is that so far we only discussed it in the multiplicative group setting, but we also need to consider in the EC setting. Then in the EC setting, you essentially need to modify the protocol, because you need a new function, and that is called hash to curve function. And that function is also very tricky. So IEEE, they started working on this function in 2000, but the solution was not constant time operation. That's why you see all these problems with the Wi-Fi, and that is because Dragonfly, they adopted this hash to curve function as defined in the IEEE standard, but that actually has side channel attack problems. So recently IETF is trying to solve this problem, but it has been going on for more than 3 years. It's not any easy problem. So if we look at the case with SPIC, then the lesson we should learn here is that when we define a protocol, we need to define it completely, not in just one setting, but all the group settings. So that will give reader the complete picture. If you only have specified in one very specific setting, then sometimes this result can be confusing and misleading. I will briefly touch on the IEEE standardization process. So this was a major effort in the community to standardize this problem, the solutions. So the IEEE P1363.2 working group was formed in 2000, At the time, people were optimistic because in the previous more than 10 years research, there are lots of papers, hundreds of papers. So people thought that the problem had been solved. All we need to do is just to review all these papers and choose some papers that are best. This shouldn't be a difficult task. So they plan it to be a 4-year project. And they review all these papers. But in the end, there are lots of arguments. It turns out that there's no PIC protocol that actually could satisfy all the security requirements. All these protocols that reviewed had various problems, various security and efficiency problems. So in 2004, there was no conclusion which one is best. And the project was extended every year until 2008. And 8 years is typically the maximum span for a standardization project. If you can't standardize a technique in 8 years, then something is wrong. 2 years ago, so in 2019, so this standard was actually officially withdrawn. So what's the problem here? The problem is sometimes it's the quantity and the quality. If you look at standardization, it doesn't really matter whether the paper, how many papers you have and where the papers are published, whether it's top conferences or other venues. What it matters is that whether the protocol proposed in the paper actually solved the problem. And although there were so many papers published and proposed, but that solution was missing. So at the end of 2008, it became clear that the PIC problem had actually remained unsolved. So that was actually a very interesting conclusion if you look at the IEEE standardization project. Okay, so I only have probably about 5 minutes before I have to go. I'll briefly touch why PIC is so difficult to get right. One of the reasons, so there's always this tension in the community about heuristic design and proof of security. So they tend to go with two separate end of the spectrum. As we know that heuristic designs are unreliable, they don't provide guarantee. So proof of security is supposed to solve this problem, but it's not that as lousy as it seems sometimes. And if you look at the field of PIC, there are many provably secure PIC protocols, but on the other hand, you also need to look at how many of these protocols have actually been implemented and used in real life. Very few. So there is a gap between the theory and the practice here. So why there is a gap? There are many reasons, but one of the reasons is assumptions in the secret proof. Sometimes people don't pay a lot of attention to the formalism of the proof, but they don't pay much attention to the assumptions. But if the assumptions do not hold water, then the proof, the value of the proof could be questionable. So everyone knows what is a random oracle. I'm not going to touch on that. There's a very famous model called random oracle model. This is proposed by Bila and Logway in 1993. There were some issues with the random oracle model because one of the steps in the proof that is heuristic. You replace hash function with a random oracle, but theoretical random oracle doesn't really exist. So a lot of papers, especially in the early 2000s, they were motivated to remove random oracle because some people don't like random oracle. So there's a whole batch of papers with a title without random oracle. So that is all fine. But then the real question is that if you remove random oracle, what else can you do? So the alternative solution is to use a common reference string, and there are a few papers on that. Basically, this model assumes a trusted third party to set up this trusted setup. But there's a catch here. The catch is how do you implement this common reference string? This is usually not discussed in the paper, but if you want to implement the paper, you have to be concrete. It was suggested in some papers that you simply use a trusted third party to define this common reference chain, but that doesn't really solve the problem, because where do you find the trusted third party? In the internet, trusted third party doesn't really exist. You trust no one. There's no third party that can be completely trustworthy. And then to solve this problem, researchers, they try to reintroduce random oracle because they don't know how to find trusted third parties. So they reintroduce random oracle to define the common reference stream. So if you read these papers, you will find that the secret proof use both random oracle and the common reference stream. So you can see it almost goes in circles. But the lesson we can see here is that you recognize a problem with model and you want to solve the problem with model by introducing a new model, but you need to be careful not to introduce new problems. And if you introduce new problems and you rely on the old model to solve new problems, then this is going in circles. There are a few examples of these protocols. The protocols based on the common reference stream. But I'm afraid I have to go because I have another meeting in 2 minutes. Sorry for that, but I only planned for 1 hour, and that meeting cannot be rescheduled or changed. So I'm happy to take any questions up to this point.
Thank you, Professor Feng. If any quick questions to Professor by any delegates, we can take it up, else he has to go for another meeting. I think you can unshare your slides.
So is it your this e-voting is that is privately is available for market?
Sorry, can you say again?
Is it available for market? Means,
which one?
You said the voting is already e-voting. You said, is it applicable for e-voting also? These things.
This is a different problem from e-voting. We also work on e-voting. E-voting is another project we are working on. We have prototype. And we are in collaboration with Bima Roy from ISI in India, trying to test the system. If anyone is interested in e-voting, feel free to get in touch. We tested e-voting in the UK, but we want to also see whether e-voting can also work in. That could be another talk.
Okay. Thank you.
There is one question from Mr. Pal that he is asking that is all security protocols will be invalid when the quantum computing comes?
That's a very good question. No, all these protocols will be broken. So finger crossed we don't have the quantum computing. That is open research question.
Okay, thank you very much, Professor Feng, and for a very outstanding talk on overview of password-authenticated key exchange protocols. A lot of new informations we have been able to get, and we will be in touch with you on behalf of CSI over mail if further question comes or any other clarification is required.
Right. Yeah.
Thank you from the organizers to you.
Thanks. Okay. Bye.
Feng. We'll meet again.
So
Thank you,
somebody
sir.
from CSI can take it over.
Yes, sir. Thank you, sir, for your valuable time to conduct this session successfully. I thank Professor Nabarun Bhattacharyya, Senior Director of C-DAC.
Thank you, sir. From inauguration to till date, you have given all the supports. Thank you, sir, for your support. Thank you.
Okay. Bye.
Bye. Diganta, over to you.
Thank you, sir.